Hi everyone, my name is Honda. Today, I will deliver a presentation about my final year project named The Demo for Power Electronics, Raman study of intrinsic and doped diamond substrates, which is supervised by Professor Richard and Dr. Joe. In recent decades, the development of smart grid makes the researches on new power electronics attract more interest. It could widely used in the factories, nuclear power plants, thermal power plants, solar power, cities and offices, and so on. All of these applications are based on the power electronics devices. Also, as there is continuous growing energy consumption in electrical energy, the role of power electronics became more and more important. By comparing the diamond with the other semiconductor material, it shows the superior electronic properties. Therefore, the diamond-based devices will become a promising approach for the next generation of power electronics. In my project, I will focusing on simulating the enhanced Raman scaling by modifying the sample characteristics and improving the quality of diamond substrate to figure out the potential application of the future device manufacturing. In my project, I choose to use two measurements to assess the quality of the diamond sample. First, it is the Raman microscope. As can be seen in Figure 2, it is the RM5 Raman spectroscopy. It is a non-destructive way to characterize the quality of diamond sample. And the basic working principle is based on the Raman scaling. The different intensity and wavelength position of Raman scaling light could feature two different peaks and generate the Raman spectrum. Each peak represents two different molecular bond vibration. Then let's move on to the figure 3. It shows atomic force microscope. It is used to measure the surface morphology of the sample, and the basic working principle of AFM is based on the atomic force between the tested sample and cantilevers. By using the optical deflection method, the change of vibration of the tip and the cantilever will be collected and processed by software. Then the graph will be formed. For the preparation of diamonds, we choose to use the microwave plasma chemical vapor deposition method, MPCVD. According to research, it is the most efficient way to grow diamonds. And for the CVD growth method, it needs a growth condition with atomic hydrogen, a gaseous source of carbon in plasma with a gas temperature about 2000 degrees. In this process, we use methane and hydrogen to produce the high-quality films. The plasma is generated by the high frequency and high power microwave, which are responsible for the growth on the substrate. By using the methodology and the measurements, I got the following results. For the diamond properties, as you can see in Figure 5, it shows the comparison of electronic properties between the diamond with the other semiconductor material. Apparently, the diamond has the best performance in all electronic properties, which indicate that the diamond grown by CVD could be a promising semiconductor material for the future demand of the high power, high frequency, high temperature suitability electronic devices. We also choose to use the figure of merit to assess the quality of diamond sample. Figure of merit is a quantity used to characterize the performance of device, system, or methods, relative to its alternatives. In my research, there are three kinds of figure of merit: the Johnson's, the Cass, and the Belligas. The FOM is used to assess the various semiconductor material suitabilities for various devices application. The results shows that the material with high Johnson's FOM is really beneficial for applying in power frequency products. The material with high Cass figure of merit presents the advantages on the behavior of thermal limit of power transistors. And finally, the high Belligas figure of merit demo illustrates its suitability for applying in high-frequency unipower devices. Then it comes to the most important part of my project, the results of Raman microscope. There are two parts of my results here. Figure A and Figure B shows the general spectrum of the single crystal sample and the bond-doped sample. And Figure C and Figure D are used in MATLAB to plot, and the data is provided by LCN. Because of the COVID-19, I cannot go to lab to do the test by myself. In Figure C, we can see that the Raman spectrum is dominated by the first order peak of 1,332 inverse centimeter. And the typical Raman spectrum and for the peak of 1,421 inverse centimeter, it is likely indicative of a D band, which may exist as a result of polishing damage of sample. In Figure D, it is the spectrum of a bond-doped diamond sample. The spectrum is dominated by the peak of 1,328 inverse centimeter. And since the sample is heavily bond-doped, the peak has a phenotype line shape, and combining that with some background fluorescence probably give rise to this type. Oh, by the way, both Figure C and Figure D are tested under the same condition with the 532 nanometer laser as the excitation source. Then let's move on to the atomic force microscope results. Figure 10 shows the surface morphology of single crystal plate samples by using atomic force microscope. And we can see that the surface roughness is very small, which means the surface is very smooth, and it is a high quantity sample, which is different to the polycrystalline diamond sample, which may have the higher roughness and some gaps in the surface. For the white spot on the graph, it is the defect of the sample, which produced in the preparation of the sample. For the diagonals on the graph, it probably is a measurement problem. If we see the scale bar on the right, here, it is very small scale bar and less than 1 nanometer. So when we measure the samples, the vibration may occur and generate some more noise, which results in some diagonals on the graph. In conclusion, through analyzing the air force microscope graph and the Raman spectrum, both single crystal sample and the bond-doped diamond sample are high quantity sample. With a deep research in EFM and Raman spectrum of diamond, it will largely improve the quality of preparation of diamond, which will help to reach the requirement of higher quality application. For example, the single crystal diamond could widely be used in the semiconductor devices and the particle detector, even in optics applications. And for the polycrystalline diamond, although there are some grain boundaries in the surface, but it is still possible to apply in the cutting tools and wire-proof tools. Then, thanks to the merits of properties, the diamond has become one of the most significant and the ideal material for power electronics devices in the future. Also, the prospects of diamond-based semiconductor devices will promote the development of smart grids. That's come to the end of my presentation. If you have any questions, welcome to email me. I'm very happy to answer that. Thank you for listening.